Hello dear student, welcome to another lecture of engineering mechanics. This is lecture number 12 and in this lecture we are going to see some more applications of frictions. Yesterday we saw the application of friction in belts and we saw the concept of rolling resistance. Now today we are going to cover the application of friction in wedges and screw jack, and let me tell you, these are very important topics. These topics were introduced in the syllabus of mechanical engineering in 2021. That means they were recently updated in the syllabus. So it means there is a high chance that you might get questions in upcoming GATE exams from these topics. So let's begin. So the first thing we are going to see will be the application of friction in case of wedges. Now what are wedges? Wedges are basically simple machines. Earlier, when we did not have sophisticated machines, in order to lift the weights, heavy weights, we developed some very basic type of mechanical machineries. And one of those machineries are wedges. Now, how the wedges work is, for example, let's say this is a heavy block which you need to lift, okay, but you want to lift it with minimum effort. So what we do is we are going to put these kind of rollers on the side, okay, in order to give it support and minimize friction, and then we will put this thing at the bottom. Now this thing has an inclined surface. This is known as a wedge. Usually these wedges are made of wood, but they can also be made of metals. Now if you push this wedge, this is the wedge, okay, if you push this wedge, then due to this inclined surface, when the wedge moves towards left, when it moves towards left, then you will see that this thing will go upward, and due to these rollers it will have minimum friction, so it will smoothly go up. So you can lift very heavy weight by applying very less load here. Now what type of questions you can expect here? So there is no concept that you need to study additionally here, okay, there will be no additional equation or formula here. You will have to use the basic equilibrium equations, but when it comes to problems of wedges, due to these inclined surfaces, the number of forces that we need to consider in the free body diagram, they increase. But in some problems what we do is, in order to reduce the number of forces, we take the normal and friction force as a single force. We will consider the resultant of normal and friction force so that the number of forces get reduced. Okay, you will see that when we will solve problems. So let's see what type of problems we can expect from wedges. Now this is the first question we have. The coefficient of static friction between the 1000 Newton body and the wedge is 0.2. So this is the 1000 Newton body and this is the wedge, okay. Coefficient of friction between these two surfaces is 0.2. Determine the magnitude of the force P required to begin raising the 1000 Newton body if the rollers are of negligible friction. So here we have to assume that these rollers are of negligible friction. There is no friction in the rollers, okay, and we are applying a load P here. In order to lift this 1000 Newton body, how much force we are going to apply here? So we are going to assume that this 1000 Newton body is just about to go up, which means there is impending sliding on this surface, okay. Now first what we are going to do is, we are going to draw the free body diagram of this blue and this pink block together, okay. So this is our block of 1000 Newton. And this is our wedge. Okay. Now, the 1000 Newton body, this will be the weight. Wedge is of negligible weight. Okay, there is no weight given, right? So we have to assume that the wedge is of negligible weight. Usually what happens is, compared to this block, the weight of the wedge is negligibly small. So we neglect the weight of the wedges. Okay. Now we are applying a force P here. Okay. Now understand. There will be one normal force from here. Let me consider this to be N1. And there will be one normal force from here. Let me write it as N2. Now some of you must be thinking that there must be a force on this surface also, like this, right? But understand this. When you push the wedge towards the left side, then this body, it will be either in contact with this wall or with this wall. It cannot be practically in contact with both the walls. Na? See, how do you get the normal reaction? How do you get this normal reaction? When this body is pushing the wall is applying equal and opposite force on the body. That's how you get this reaction. Now the body will either push this wall or it will push this wall. How it can push both the walls? Is the body expanding? No, it is a rigid body. It is not expanding. So when you apply a force on the wedge, it will either push this wall or that wall. Now a little bit of common sense will tell you that the wedge is going to push this wall, right? If you apply force towards left on the wedge, it will be pushing this wall. So you will get the normal reaction on the body only from this side. Okay, you will not get the normal reaction from both the sides because the body is not expanding, right? So I am getting only this normal reaction. Now there will be no friction force on this surface and this surface, okay? And right now, as this body and this body, they are connected together, there are no forces on this surface. If you are thinking there will be friction force on this surface, there will also be normal force on this surface, but both the bodies are connected right now. So I will not show the force on this surface. Okay. Now here, how many unknown forces do you see? You see three unknown forces, P, N1, N2. And how many equilibrium equations do you have? You have only two equilibrium equations. Summation of fx equals to 0 and summation of fy equal to 0. There is no summation of m equal to 0. Why? Because you don't have the dimensions of the body, you don't know the distances of these forces, so you can't take the moment here. So you have only summation of fx equals to 0 and summation of fy equal to 0. Summation of fy equal to 0 will give you N1 equal to 1000 Newton, right? And summation of fx equals to 0 will give you P equal to N2, right? Now understand how I am going to solve this problem. So from summation of fy equal to 0, N1 will be equal to 1000 Newton. So I have got the value of N1. Now what I am going to do is, I am going to draw the FBD of only this one, this wedge, and from there I will get the value of P. Okay, so this is P, this is 1000 Newton, right? N1 is equal to 1000 Newton, we have just calculated. Okay, and now as we have isolated the block from the wedge, there will be normal and friction force on this surface, right? So the normal force will be like this, normal to the surface. Let me call it N3. And friction force will be in which direction? See, we are assuming that impending sliding is about to happen on this surface, na? So this wedge is moving towards left, so the friction force will be towards right, like this. Parallel to the surface. What will be its value? 0.2. Mu is 0.2, so it will be 0.2 N3. Okay, now understand this. Look at the angles. Do you have the angles? Yes, we have the angles. This angle is how much? This angle is 15 degree, right? It is given. The angle of the wedge is 15 degree. So this angle is 15 degree. Now if the surface is making 15 degree with horizontal, if the surface, this inclined surface is making 15 degree with horizontal, then the normal to the surface, N3 is the normal to the surface, na? So if the surface is making 15 degree with horizontal, then the normal to the surface will make 15 degree with vertical. Yes. So this angle will be 15 degree. Okay. Now understand. You have two choices here. You can either use summation of fx equals to 0 and summation of fy equal to 0 here. Okay, because there are only two unknowns, P and N3. So summation of fx equals to 0 and summation of fy equal to 0 will give you the value of P. Or what you can do is, you can take the resultant of N3 and mu N3. Take the resultant of N3 and mu N3, okay? And then you use Lamy's theorem. You can apply Lamy's theorem, because then there will be only three forces, P, 1000 Newton, and the resultant of N3 and mu N3. Now we will choose the second option, because I want you to understand the concept of this, taking the resultant. This is the resultant of N3 and mu N3. Let me call it R3. Okay. Now understand this. Understand this. The angle between R3 and N. The angle between R3 and N is equal to phi. This angle is phi. See, this angle is 15, the angle of vertical and N3, and this angle is phi. Okay, so what is phi? Phi is friction angle, tan inverse of 0.2. So phi will be how much? 11.31 degree. Okay. So this angle is 11.31 degree. So now understand this. Now you have this thing. P horizontally towards the left, then 1000 Newton vertically upwards, and you have R3, which is making phi plus 15 degree with vertical. Phi is 11.31. So this is the angle between R3 and N3, and the angle between N3 and vertical is 15 degree. So this total angle between R3 and vertical will be phi plus 15. Yani ki means 11.31 plus 15, 26.31. This angle will be 26.31. Okay. So this is P. This is 1000 Newton. This is R3. Okay. This is 90 degree. This is 90 degree. And this will be how much? 180 minus 26.31. 153.69 degree. So now what we can do is we can apply Lami's theorem and we'll get the value of P. So P divided by sine of angle between 1000 and R3 is 153.69 equal to 1000 divided by sine of angle between this and this is 90 plus 26.31. So from here I am going to get the value of P. So it will be 1000 sine 153.69 divided by 494.45 Newton. So this is the minimum effort required to move this block. So you can say that in order to move the 1000 Newton block, you are applying an effort of 494.45 Newton. Let's move on to the next question, and this is our next question. A 200 Newton block rests as shown on a wedge of negligible weight. The coefficient of static friction is 0.1 at both surfaces of the wedge, and friction between the block and vertical wall may be neglected. Find the minimum force required to move the block. See, here we have a 200 Newton block. This is a block of weight 200 Newton, and the wedge is of negligible weight. Coefficient of friction is 0.1 at both surfaces of the wedge. So we have friction on this surface as well as on this surface, and friction here will be neglected due to rollers. Okay, and now we need to find the minimum force P required to move the block. Okay, so what we are going to do is, if we draw the free body diagram of both these bodies together, if we draw the free body diagram of both these bodies together, then what we are going to get? It is something like this. weight of the block is 200 Newton. This is force P. Okay. Now there will be one normal reaction from here. There will be one normal reaction from here. Okay. And there will be friction force here. Okay. Here on this surface, we are not going to consider any normal and friction force in this free body diagram because both the bodies are connected together. Okay. But here you will get friction force, right? Now, if the wedge is about to move towards right, due to impending sliding, the friction force will be towards left. So this is P. This is 200 Newton. Let me call this N1. This is N2 and this is mu N2. What is mu? 0.1. Okay. Now here, if I apply summation of Fy equal to 0, I will get N2 equal to 200 Newton, right? N2 is equal to 200 Newton here. Now I need to find the value of P. Summation of Fx equals to 0 is not going to give me value of P. So what I need to do? I need to draw the free body diagram of this wedge separately. Okay. Just like in the last problem, we will draw the FBD of the wedge separately. So this is how much? N2 200 and this is 0.1 N2 means 20. Okay, this is P. Now here on this surface you will get a normal reaction and a friction force. Yes. So let's draw the normal reaction and the friction force. The normal reaction will be like this. So this is N3 and friction force will be, the wedge is going towards right, so friction force will be towards left. So this will be 0.1 N3, 0.1 on both sides. Yes. Now again you have two choices. You can either use summation of Fx and summation of Fy, or you can use Lami's theorem. If you are using Lami's theorem, you will have to find the resultant of 220. Okay, and it will be at phi angle with 200, and then you'll have to also find resultant of N3 and mu N3. Okay, it will be at an angle phi. Okay, or you can use summation of Fx and summation of Fy here. Okay, now in the last problem we use the resultant concept. Here we will use summation of Fx, summation of Fy, so that you get the taste of both the methods. Okay, now understand, this N3 is making 15 degree with vertical, because this is making 15 degree with horizontal. Yes, this is 15 degree, so this will be 15 degree. Okay, Now carefully you have to resolve the forces, okay? So first we will use summation of Fy equal to 0. In y direction, there is 200 Newton upward, then there is cos component of N3 downward and sine component of 0.1 N3 upward. So it will be something like this, 0.1 N3 sine 15 plus 200 minus N3 cos 15. So from here you get the value of N3. It will be 200 divided by cos 15 plus 0.1 into sine 15. So I am getting 201.65 Newton. Okay. So we have got the value of N3. Now using summation of Fx equals to 0, we will get the value of P. So if I apply summation of Fx equals to 0, what I am going to get? See, P is towards right. So it will be P, then 20 Newton is towards left. So minus 20, then N3 sine 15 will be towards left. So minus 201.65 sine 15 and then 0.1 N3 cos 15. So minus 0.1 into 201.65 cos 15 equal to 0. So by solving this equation, you will get the value of P. 20 plus 201.65 sine 15 plus 0.1 into 201.65 cos 15. I am getting around 91.67 Newton. So this is the answer. P is around 91.67. So these type of problems you might get from wedges. Okay, you just need to be careful with the friction forces, and if you are considering the resultant, you need to be careful with the angles. Okay, chalo. So this was the first application of friction for today. Now let's move on to the next application of friction. And this next application of friction is known as screw jack. Now what do we mean by a screw jack? See, I told you that earlier when we did not have sophisticated devices in order to lift heavy weights, we use simple machines. Okay, one of those machines is known as pulley, then we have wedges, and now we also have screw jacks. Okay, compared to wedges and pulleys, these are more sophisticated. Okay, these are more advanced. Here the effort required to lift heavy weight is reduced drastically. For example, in order to lift 1000 Newton, you will need only 10 Newton in case of screw jack. So the effort required to lift heavy weight is reduced that much from 1000 to 10. Okay, now in case of screw jack, there is a screw which you need to rotate in nut. This is the nut. Okay, so if you rotate the screw in this nut, then this screw is going to go up or down. Now, in order to rotate this nut, you will apply a force like this. Okay, for example, this is a screw. In order to rotate the screw, what I am going to do, I am going to apply a force like this. Okay, on the surface of this screw. So if I apply a force on the surface of the screw, this force is going to rotate it like this, na? Hai na? If I apply a force on the surface of the screw, it is going to rotate the screw. But what happens is, it is not that effective. So what we do is, we put a lever on the screw. You can see that this is the head of the screw and we have attached a lever. So instead of applying a force on the surface of the screw, we are going to apply the force here. So when this force will rotate the screw, we'll get much more effort. Are you getting what I am saying? See, in order to lift the weight using this screw, we need to rotate the screw. Okay, in order to rotate the screw, we need to apply force on the surface so that there will be a torque which will rotate this, and there will be a moment which will rotate this. But if I apply a force directly on the surface of the screw, the moment that it will create will be very less. But if I apply a force on the lever, then the moment will increase too much because of this distance. So that is why we are going to use a lever like this. Okay. Now let's understand about the screw first. Let's understand the nomenclature of the screw. So this is the screw which has square threads. These are known as threads. Okay. There are threads on the screw, then there are threads on the nut. And these threads, they combined, and then when you apply the force, it rotates. Okay, just like the bottle, the cap of the bottle. Okay, here I have the bottle. So you can see that there are threads on this bottle also. These are the threads. I hope you can see. And then there are threads in the cap also. Okay. So when I put the cap on the bottle, the threads meet. And now I apply force. Now we don't have a lever. So what I am going to do, I am going to apply force directly on the surface like this. So now it is rotating. See? And it is lifting up. You can see. If I apply force like this, it is lifting up. Can you see? Okay. So just like that, screw jack also works. Okay. Now, the nomenclature of the screw. So these threads are of different shapes. Here we are considering square threads. Square threads means they are cut like this. Okay. Now understand different parameters of this thread. So this square thread has a maximum diameter and a minimum diameter. See, this DM is known as the major diameter, which is the maximum diameter, and DC is known as the minimum diameter, which is the core diameter. Okay, so maximum diameter, minimum diameter, and D is known as the mean diameter, which is the average of maximum and minimum. So whenever we are making calculations now, we use the mean diameter, not the maximum or minimum. We are going to use the mean, average of maximum and minimum. Okay. Now these threads are at an angle. You can see here. They are inclined at an angle. This angle is known as helix angle. Let me call it theta. So this theta is known as the helix angle. Okay. Now you can see that the distance between the adjacent threads, this is one thread, this is the next thread. So the distance between the adjacent threads is given as P, which is known as pitch. What is pitch? It is the distance between the adjacent threads. Okay. And distance between adjacent threads. And then there is lead. Now what do we mean by lead? When you rotate this screw is going to move up or down, means in axial direction. If you rotate the screw one time, how much it is going to move upward or downward? That is known as lead. So what is lead? Axial distance moved by screw for one rotation. Okay. Now if you have a single threaded screw, what do we mean by single threaded screw? Single threaded screw means, see, what is this thread? You can assume that we have wound a wire on a rod. So if you have a single wire and then you wound it on the rod like this, then it will be known as a single threaded screw. And if you have two wires, you combine them and then you wound it on the rod, then it will be known as a double threaded screw. Okay. Here we have a double threaded screw. How do I know? You can see this is one single thread. Okay, it is coming down and now again here, and in between this we have another thread. Can you see? This is one single thread, but in between this there is another thread. So this is a double threaded screw. So in case of double threaded screw, L will be equal to 2P. So you can say that L is equal to N into P, where N will be equal to 1 for single threaded screw and N will be equal to 2 for double threaded screw. Okay. If nothing is mentioned, assume that it is a single threaded screw. Okay. Now understand this. In case of screw jack, we need to find out, in order to move this weight, how much force we need to apply on the lever. Okay. In order to lift the weight, in order to move the weight either upward or downward, how much force we need to apply on the lever here. But we will not be able to find the force required directly on the lever. First we will find the force required on the screw. Okay. See, this is the screw. So if we apply the force directly on the screw, like this, then how much effort is required? And from there we will calculate the effort required to be applied on the lever. Okay. Now understand how we are going to find that. Look at here. This is the screw. and this is the nut. Can you see? This is your nut. The screw is rotating inside the nut. Okay. Now consider one thread. You can see this is one thread. Okay. It is rotated like this. Okay. Now consider 2 points A and B on the adjacent thread. Okay. We need to find out how much effort we need to apply to move this from here to here. We need to give it one complete rotation, right? We need to give it one complete rotation. So we are moving the screw from here to here. Okay. This is known as the lead. Now, in order to understand it better, what I am going to do is I am going to open it. Okay. This one single thread na, I am going to open it. Look at it. Look at it. I have deleted all the other parts and now you have only the thread from A to B. Okay. If I open it, it will look like this. Okay. Now understand it. Rotating this screw from A to B, how much effort do you require? But this screw has a weight on top of it, right? The screw jack is used to lift heavy weight, na? So that weight is resting on top of it like this. Okay. So if you rotate this screw has to go from A to B, but there is a weight resting on it. I can assume that the weight is just like this. Okay. It is just like a block, which is right now here. Something like this. You have a block of weight W, which is right now here, and you need to move this block from A to B. Okay. You have a weight like this. And you need to move it from A to B. Okay. By applying a force. And where are you applying the force? You are applying the force here on the surface of the screw in order to rotate the screw. Okay. Now understand. Can you calculate this angle theta now? Yes, you can calculate this angle theta. This angle theta will be tan inverse of L divided by 2 pi r. See, what I have done is I have unwrapped this thread from A to B. So it became like a triangle. Okay. What is this distance? This will be equal to the lead. If it is a single threaded screw, it will be equal to the pitch. But if it is a double threaded screw, the lead will be 2 times of pitch. So what is this? From A to B, what is the height? This height is equal to the lead L, and this will be 2 pi r, where r is the mean radius. You can also write it pi d. You can write it pi d. Mean diameter. Okay, so it will be tan inverse of L by pi d. So we now have this helix angle. Okay, this formula you need to remember. This is the formula of finding the helix angle. Theta equals to tan inverse of L by pi d. Okay. Now understand. We need to find out how much effort we need to apply on the screw in order to move this block from here to here. Okay. So now understand. It is something like this. This is your thread. And this is the block which is kept on the thread. And now we are applying a force like this in order to raise it from A to B, right? In order to move it on top of this thread. Okay. Now understand. This is the weight W which we need to raise. Now there will be a normal force between the block and the thread. That normal force will be acting something like this, N, and there will be a friction force. So if you assume that it is just about to go up, the friction force will be down like this. Okay. Now we need to find the value of P. This angle is theta. Okay. Now if the surface is making angle theta with horizontal, the normal will be making angle theta with vertical, right? So this angle will be theta. Let me make it with another color. Okay. Now understand it. You can either use summation of fx and summation of fy to calculate P in terms of W, or what you can do is you can take the resultant of n and mu n. So let's say this is the resultant of n and mu n. This is R, and this R is making the angle phi with normal, right? Friction angle is the angle between resultant and the normal force. So now this resultant is making theta plus phi with vertical. So now you have three forces. P is horizontal, W is vertical, and then you have R making an angle theta plus phi with vertical. Okay. So now you can apply the Lamy's theorem here. This is P, this is W, this is R. So if you apply Lamy's theorem, what you are going to get? P divided by sine of 90 plus phi plus theta equals to, sorry, let me do it on the next page. P divided by sine of 90 plus phi plus theta, sorry, it will be 180 minus phi plus theta. equal to W divided by sine 90 plus phi by theta. Now sine 180 minus some angle is sine of that angle. So this will become sine phi plus theta, and sine 90 plus some angle will become cos of that angle. So if sine goes here, it will become 10, na? So it will be P equals to W 10 phi plus theta. So this is the force required to raise a weight W on the screw jack, okay, where W is the weight, phi is the friction angle, and theta is the helix angle. Phi is tan inverse of mu and theta is tan inverse of L by pi d. You have the angle theta, formula of angle theta, right? Tan inverse of L by pi d. So you need to remember this formula as well as this formula. But this is the effort required to raise the weight. The effort required to lower the weight. How we can calculate this? You will have the same diagram, but this time you need to lower the weight. So this time we are going to apply a force like this to lower the weight. This will be the normal force and this will be the friction force. If it is going up, na, sorry, down, na, so friction force will be up. This is P, this is W, this is N, this is mu N. Okay. Now this time, if I consider the resultant, this is going to be the resultant. This is R. Okay. Now understand, this is the angle theta. So the angle between the vertical and N is theta, and the angle between R and N is phi. So what will be the angle between R and vertical? Phi minus theta. Look at this, the angle between N and vertical is theta, the angle between R and N is phi. So what is this angle? The angle between resultant and vertical, it will be phi minus theta. So if I draw the diagram, in this case, this is P, this is W, and this is the resultant, and this is the vertical. P, W, sorry, W, resultant, this is the angle phi minus theta. Okay, so here if I calculate the same angle, I will get same formula, I will get PW 10 phi minus theta. You can do it just like this. Okay, you will get the same thing, but this time it will be phi minus theta. So this is the effort required to lower the weight. Okay. Now understand this fact. What we have calculated right now is the force required to lower the weight. In this formula, this value can never be 0. But here you can see that if phi becomes equal to theta, then this value will become 0. Now what does that mean? It means that if phi becomes equal to theta, P will become 0. If phi becomes equal to theta, P will become 0. Areva, it is good. We don't need any effort in order to lower the weight. No, it is bad. Why it is bad? because if phi becomes equal to theta, no effort is required to lower the weight. P is equal to 0. So weight automatically starts going down. Do you need that? Do you want that? Do you want the weight to automatically go down? No, na? You have raised the weight to a certain height and now you are not applying any effort. But in order to go down, it doesn't need any effort. So it will automatically go down. So we don't need that. We need self-locking. What do we mean by self-locking? Self-locking means it will be locked in that position. If I am not applying any effort, it will be locked in that position. So for self-locking, this phi should always be greater than theta. This is a very important concept, okay? If this phi is greater than theta, then you will always get some positive value here. Means in order to lower the weight, you need to apply some force. If you don't apply that force, it will not go down. It will be locked. But if this phi becomes equal to theta, it means it will automatically start going down. P will become 0. It will automatically start going down. So self-locking means if we don't apply any effort, it will automatically be locked. Okay. Now understand this. Whatever effort we have calculated, that effort is applied on the surface of the screw like this. Okay. If I attach a lever to it, then how much effort I will be required? Like this. Understand this. Consider this situation. And then this situation. This is the center, okay? So in one case, I am applying force directly on the surface, and in one case, I am applying force here on the handle. Okay. What is this distance, beta? This distance is d by 2. What is this distance? This is L. In both cases, we are practically applying some torque, na? Okay. So here this is, let's say, P, and here this is, let's say, F. So we have calculated P. Now what if we need to calculate F? So instead of applying force here, we are applying force here. But in both cases, what we need? We need this torque, basically. Okay. So I can say that F into L, whatever torque is generated here, same torque has to be generated here. So from here, you can find out the force F. Okay. Efficiency of a screw jack. Now what do we mean by efficiency of a screw jack? Understand this. Efficiency of a screw jack, eta, is output work per rotation divided by input work per rotation. Understand? What we are doing is, efficiency is output divided by input, but here we need the output and input per rotation. Okay. So efficiency will be output work done per rotation of the screw divided by input work per rotation of the screw. Now what is output work per rotation? What is our output? We are lifting the weight W, that is our output, na? And that W, how much it is lifted in one rotation? By L, lead, right? In one rotation the screw is lifted by L, so the weight is lifted by L. So what is work done? Force into distance, so W multiplied by L. This is your output work done in one rotation. Now what is your input? You are applying the force P, right? And that force P, how much it is moving? How much it is moving? You are moving the force by this distance, na? We are applying a force like this and it is moving from A to B by this distance, pi d. So what is your input work? Force into distance, P into pi d. Now what is the value of P? If we consider that we are finding the efficiency of lifting the weight, then P will be W tan phi plus theta. Okay. Now W and W will be cancelled. What is L by pi d? L by pi d is tan theta, na? So this will become tan theta upon tan phi plus theta. So this is the efficiency of a screw jack. So you need to remember this formula, this formula, this formula and this formula. Okay, you need to remember the formula of theta, which is tan inverse of L by pi d, and you need to remember the formula of P, and then you need to remember the formula of efficiency. Okay, let's solve a problem here. A screw jack has mean diameter of 50 mm and pitch 10 mm. If coefficient of friction is 0.15, find the effort at the end of a 700 mm long handle to raise a weight of 10 kilonewton. So here what is given? We have the pitch diameter, sorry, we have the mean diameter 50 mm, we have the pitch, which will be considered as lead because nothing is mentioned, na? Coefficient of friction mu is 0.15 and the length of the lever is 700 mm and W is 10 kilonewton. Now we need to find the force F at the end of the lever. First we will calculate P. So how do we calculate P? We need theta and phi. So phi will be tan inverse of mu, which is 0.15. So it is 8.53 degree and theta is tan inverse of L by pi d. Okay, which is lead. Okay, sorry, this L and this L is different, na? Let me write it something else, S. Okay, so this is tan inverse of 10 by pi into 50. So what is theta? (3.64 degree). So P will be equal to W tan phi plus theta. So it will be 10 kilonewton into 10, 8.53 plus 3.64. So we'll get the value of P. 2.15 kilonewton. But we need the force required at the end of the lever. So it will be like this: force into length of lever equal to this force into radius. So how much is this force? 2.15 kilonewton, na? So 2150. So from here you will get the value of F. You are getting 76.78 Newton. So you can see that in order to lift a weight of 10 kilonewton, you are applying only force of 76.78 Newton. So by this much amount, your effort is required. So you can understand how efficient the screw jack is in lifting weights, right? Now this is your assignment and I expect you to solve this. In tomorrow's class, I will give you the answer. Okay? Chalo. So that's it for today's class. Thank you so much. I will see you guys tomorrow. From tomorrow, we are starting a new topic, a new chapter, which is truss and frames. So I will see you tomorrow at the same time. Bye-bye. Take care. Good night.